All right, class, welcome. Today, we're going to do something kind of cool. We're going to peek inside a device you probably use every single day without even thinking about it, your phone charger. I know, it seems like just a simple little block, right? But the engineering packed inside is, well, it's fundamental to pretty much all modern electronics. So let's get started and see what really makes it tick.
So let's start with a really simple question. You've probably wondered this at some point. The wall socket has all the power you could ever need, so why this little middleman? Why do we need this adapter? Why can't we just hook our phone straight into the wall? Well, the answer comes down to a fundamental clash between two very different kinds of electricity.
Okay, so here's the core of the problem. On one side, you've got the wall socket. It provides what we call alternating current, or AC. Just picture a wave that's constantly flipping its direction back and forth 60 times a second. It's kind of wild. But on the other side, you've got your phone, and honestly, almost every piece of electronics you own. It needs direct current, or DC. And DC is the complete opposite. It's a smooth, stable current that only flows in one direction. Trying to run your phone on AC power would be like trying to water a delicate little plant with a fire hose. It's the wrong kind of power. It's messy, and it just wouldn't work.
So, we've got this big problem, right? We have this chaotic, wavy AC power from the wall, and our phone is begging for this calm, smooth DC power. How do we fix this? We need some kind of translator, a component that can take that wild AC and tame it into a clean DC signal that our devices can actually use.
And this is where the hero of our story comes in, the p-n junction diode. Now, the name sounds complicated, I know, but the idea behind it is incredibly simple. Think of it like a one-way street for electricity, or maybe like a bouncer at a club door that only lets people go in but never out. Current can flow through it one way, easy peasy, but if it tries to go the other way, nope, the door is shut. And that one simple trick is the key to everything. Okay, so let's dive in and really understand this one-way street. Let's see how it's built and, more importantly, how it actually pulls off this bit of electronic magic.
So what's a diode actually made of? Well, it's made by squishing together two specially treated types of semiconductor material, usually silicon. On one side, we have what's called p-type material. Think of it as having a bunch of little empty parking spots, or holes, where electrons should be. These holes act like positive charges. On the other side, we have n-type material. This stuff has been treated to have a bunch of extra free electrons just floating around, ready to move. These are our negative charges. The real magic happens right at the boundary, the junction where these two different materials meet.
Now, just having that junction isn't enough. The real control, the secret sauce, comes from how we apply voltage to it. Now listen up, because this concept is absolutely critical, and I can almost guarantee you'll see this on your exam. It's called biasing.
First up, let's look at what we call forward bias. This is what happens when you connect our battery the right way. We connect the positive terminal to the p-type side and the negative terminal to the n-type side. What happens? Well, that external voltage literally pushes the positive holes and the negative electrons right toward each other at the junction. They overcome the natural barrier there and, boom, the gate swings wide open. Current can now flow right through the diode with almost no problem at all.
So, what happens if we flip the battery? This is what we call reverse bias. Now we connect the positive terminal to the n-type side and the negative to the p-type. You can probably guess what happens. It does the exact opposite. It pulls the electrons and the holes away from the junction, making that barrier in the middle even bigger and stronger. And bam, the gate slams shut. Essentially, no current can get through. It's completely blocked. And this graph? This is the perfect picture of everything we just talked about. This is called the VI, or voltage current characteristic curve. Look on the right side, in the forward bias region. You see that? Once we apply just a tiny bit of voltage, the current shoots straight up. It flows freely. Now look at the left side, the reverse bias region. See how the current stays flat, right near zero, no matter how much negative voltage we apply? It's blocked. This graph is the perfect visual summary of our one-way street. Okay, so we have our one-way gate. We understand how it works. Now, let's finally connect all of this back to our original problem, that phone charger. Let's see how this little component actually turns that wavy AC into smooth DC.
The circuit that performs this magic trick has a name. It's called a rectifier. And its whole job, its entire reason for existing, is to take that alternating current, AC, and turn it into direct current, DC, using our new best friend, the diode. This circuit, this is the real heart of your phone charger.
The simplest version is called a half-wave rectifier. Remember how AC goes positive, then negative, then negative? Well, we just stick a single diode in its path. So when the AC wave is positive, the diode is in forward bias, the gate's open, and it lets that positive part pass right on through. But the instant that wave tries to go negative, the diode flips into reverse bias, the gate slams shut, and that entire negative half of the wave is just blocked, chopped right off. We've gotten rid of the part that was going in the wrong direction. But wait a minute. Look at the output there. See all those big empty gaps? By just chopping off the negative half, we are literally throwing away half of the energy we're pulling from the wall socket. That is incredibly wasteful. There has got to be a smarter way to do this. And of course there is. This brings us to the full-wave rectifier. Now this is much more clever. Instead of just blocking the negative half of the wave, a smart arrangement of diodes actually inverts it. It flips it upside down and makes it positive too. Now look at that output waveform. We're using both halves of the AC cycle. No more wasted power. It's a much more efficient and much more elegant solution. All right, let's hit pause for a second. I want you to pay really close attention to these next two slides. This is the stuff that is extremely important for you to understand, especially when it comes time for your exams. This is the core, distilled knowledge you need to have locked in. This table tells the whole story. Just look at the numbers. Let's start with efficiency. The half-wave rectifier, only about 40% efficient. You're throwing away more power than you're using. But look at the full-wave and bridge rectifiers, over 81% efficient. That's more than double. Now look at the ripple factor. Just think of that as how bumpy or wavy the final DC output is. A lower number is way better. The half-wave is at 1.21, very bumpy. But the full wave is down at 0.482. That's a much smoother, higher quality DC output. So the takeaway is simple. Full wave is vastly more efficient and gives you a much cleaner signal. And finally, let's do a lightning round recap of the essential vocabulary. You've got to know these terms. PN junction, that's the boundary, the heart of the diode. Biasing, that's just applying an external voltage to it. Forward bias means the gate is open, current flows. Reverse bias, gate is closed, current is blocked. The whole circuit itself is a rectifier. And this last one, Zener breakdown. We didn't go deep on it today, but it's an important concept, where a special diode is actually designed to conduct in reverse at a very specific voltage. It's super useful for regulating voltage, and we'll definitely explore that in a future lecture. So, there you have it. We've seen how this simple one-way gate, the diode, is the real secret inside your phone charger. But this concept is really just the beginning. The diode is a fundamental building block for countless other electronic circuits. So I'll leave you with a question to chew on. Now that you understand this core principle, what other kinds of electronic magic do you think it makes possible? That's all for today. Thanks for your attention, everyone.